Good morning, my dear students. In today's class, I am going to discuss about delay line cancellers. The delay line canceller acts as a filter to eliminate the DC component of a fixed targets and to pass the AC component of the moving targets. And then this is the block diagram of the delay line canceller. And this delay line canceller consisting of one delay line and a subtractor. The subtractor has two inputs. One is the normal input and another one is the time delayed input. Already we know from the basics of this CW radar or MTA radar, the fixed target will provide a constant amplitude or equal amplitude. By subtracting the equal amplitude, we get the 0. That means the stationary targets are eliminated by using the subtractor, and only the moving targets will give the voltage here. And then the bipolar signal is converted into unipolar by using a full wave rectifier for the display purpose. If you use the plane position indicator, we require a unipolar signal. And there are two types of delay line cancellers are there. First one is time domain delay line cancellers and second one is frequency domain delay line cancellers. And the advantage of the time domain delay line canceller is it uses a single network. It operates over all ranges and does not require a separate filter for each range. And the filter characteristics of the delay line canceller is the delay line canceller will act as a filter and it eliminates the DC component of a fixed targets. And because of the periodic nature, the filter also rejects the energy in the vicinity of the pulse repetition frequency and its harmonics. Suppose the video signal received from a particular target at a range of R0 is V1 equal to K sine 2 pi f dt minus phi naught, and the time delayed version of the signal is V2 equal to K sine 2 pi f t minus Tp minus phi naught. Both signals are given to the subtractor and subtractor output is V1 minus V2, that is equal to 2K sine pi f dt p cos 2 pi f t minus Tp by 2 minus phi naught. And the magnitude of frequency response of a delay line cancellor shown below. By observing the frequency response of a delay line canceller, the response is 0 at the pulse repetition frequency and multiples of the pulse repetition frequency. And the next concept is blind speeds. The blind speeds are the relative velocity of the target which results in a 0 MTA response are called blind speeds. The blind speeds are occur when pi into fd into Tp equal to plus or minus n pi. From that we can get fd equal to n by Tp, that is equal to nfp. That means blind speeds occur when fd equal to n into fp, where n equal to 0, 1, 2, 3. The delay line canceller not only eliminates the DC component of the fixed target and also rejects the any moving target whose Doppler frequency shift happens to be same as pulse repetition frequency or multiples of the PRF. From this we can calculate the blind speed. The blind speeds is given by, we know Doppler frequency shift fd equal to 2 Vr by lambda. Here it is replaced by the blind speed Vn. And this blind speed will occur when fd equal to nfp From this, Vn equal to n lambda by 2 Tp, that is equal to n lambda Fp by 2, where n equal to 1, 2, 3. And the next concept is double cancellation. The frequency response of a single delay line canceller does not have a broad clutter rejection in the vicinity of the DC, and the cluster rejection notches are widened by passing the output of delay line canceller through second delay line canceller. In double cancellation, in double delay line cancellers, two single delay line cancellers are connected in cascade. Therefore, the frequency response of double delay line canceller is square of the single delay line canceller, so that we can get frequency response is 4 sin square pi fd t. This is the first figure is the double delay line canceller. Here two single delay line cancellers are in cascade, and the same response is obtained with the below figure. This below figure is also called as a 3 pulse canceller, but weights to the summer is changed. The output of the double delay line canceller is given by f of t minus 2 f of t plus t plus f of t plus 2t, and same response is obtained with 3 pulse canceller. By observing the frequency response of a single delay line canceller and double delay line canceller, you can get the basic understanding. And the solid line indicating the single delay line canceller frequency response, and the dotted line indicates double delay line canceller frequency response. By observing this double delay line canceller frequency response, we can say the cluster rejection notches are widened. And the next concept is staggered pulse repetition frequencies. Suppose the blind speeds of the two independent radars operating at same frequency will be different if pulse repetition frequencies are different. Therefore, if one radar blind to the moving target, other radar may be not blind. And same thing will occur. Instead of using two separate radar, the same result obtained by one radar with two pulse repetition frequencies on time shared basis. This is called a multiple PRFs. The pulse repetition frequency might be switched on each scan, or every time when antenna scanned a half beam width, or the period might be alternated on the every other pulse. When the switching is from pulse to pulse, it is known as a staggered pulse repetition frequency. When the pulse repetition frequency is changing from one pulse to other pulse, that type of switching is called a staggered PRFs. The composite response of MTI radar operating with two separate pulse repetition frequencies on time shared basis is shown below. The first figure is the frequency response of a single delay line canceller with a pulse repetition frequency of 1 by T1, and the second one is it is the frequency response if the pulse repetition frequency is 1 by T2, and third figure is the frequency the composite response of a MTI radar with the staggered pulse repetition frequencies. On one pulse we are using a pulse repetition frequency of 1 by T1. On other scan we are using a pulse repetition frequency of 1 by T2. Because of this, we are going to reduce the blind speeds. Here the blind speeds are reduced, and then the value of the first blind speed also increases. The pulse repetition frequencies are in the ratio of 5 is to 4, and the composite first blind speed increases several times compared to single pulse repetition frequency, and the zero response occurs when blind speeds of the each PRF will coincide, and blind speeds are occur when 4 by T1 equal to 5 by T2, and the closer the ratio of T1 by T2 approaches the unity, greater will be the value of first blind speed. This is about the staggered pulse repetition frequencies, and by using the multiple pulse repetition frequencies, we can reduce the or minimize the effect of blind speeds. This is about the staggered pulse repetition frequency MTA radar. Thank you very much.